Well, hey folks, Mr. B again. So today's lesson is going to be on isotopes. So I've gone back out to our fancy periodic table, and the reason I'm here is because if you look at hydrogen's atomic mass, you would figure, hey, hydrogen has one proton. So if it only has a proton and electrons don't really weigh anything, it's negligible, then why isn't its mass 1? Well, when you look at the atomic mass of hydrogen right there, you'll see 1.008. And that's a little indication that there are other kinds of hydrogen out there. Now, they're all hydrogen. They've got one proton. But when we think back to how we've been studying the nucleus and what we've learned about it, there's not just protons in there. There's neutrons. Neutrons provide weight. They don't change what kind of element you're talking about, but they do provide weight. So, something to show you here. Little did you know that there's 3 types of hydrogen. Sort of lightweight, medium weight, and then heavyweight hydrogen. The hydrogen that you know and love is on the left. Now, there's an older name here called protium, and you'll see that the H has a superscript 1 above it. That means that's the hydrogen that weighs 1 atomic mass unit. In the middle is something called deuterium, which you see in some nuclear reactors. We'll get to that later. This is hydrogen, but you notice that there's a neutron in the nucleus. Now, if you have a proton and a neutron, your atomic mass is 2. Move over to tritium. Now, if we add a second neutron in there, we have 3 particles in the nucleus. It weighs 3. Now, it's still hydrogen because there's 1 proton, but it has an atomic mass of 3. So going back, you might wonder, all right, if these are the 3 different masses of hydrogen, 1 atomic mass unit for protium and 2 for deuterium and 3 for tritium, why do we see that strange number 1.008? Well, the simple answer to this question, you guys, is that you have to think about how much deuterium and tritium actually exist in the universe. And there isn't as much. So because those other 2 forms are a lot more rare, you're seeing an average weight for the hydrogen that we find. So average weight gives you that really small 1.008, and that tells you the alternative forms of hydrogen, that being deuterium and tritium, are a lot more rare. We have to talk a little bit more about isotopes, but what I wanted to preface this with is that this is all hydrogen. It's just that it weighs different amounts. And that's what isotopes are. Same element and weigh different amounts, right? And that's like people. People are people, right? We can weigh different amounts. Nothing wrong with that. Okay, so over to my little show here today. So an isotope is got the same number of protons but a different number of neutrons. So let's put some flesh on the bones here. So let's take carbon, right? Now carbon, we'll just put little pluses in the inside there, and you'll see that there are 6. Carbon, well, that makes sense, right? It's atomic number 6. Let's jump out to our periodic table, make sure that's true, right? So atomic number 6, we go out to carbon. There it is in the purple, second row, atomic number 6. Okay, that being said, where does this take us? Well, we'll put in O's for neutrally charged particles, right? So we'll let the O's be the neutrons. And what we find is that carbon has a mass of 12 atomic mass units. Now that's not quite true because there are other kinds of carbon, but we'll look at this one and we'll say it weighs 12 atomic mass units. Now, remember that the number of protons, right? Protons are equivalent to the number of electrons. So we have 6 protons, and that's equalized by 6 electrons, right? So we're looking at an atom here. This is neutral, and I keep harping about this point. It's neutral. Ions are when atoms aren't neutral. Okay, so this is the carbon we expected to see. We call this carbon-12. Oop. I just have to restart there. So let's populate this again. Proton 6, neutron 6, for a grand total of, wait for it, drum roll, 12. Okay, that's how mass works. Remember how you can work backwards, right, to find the number of neutrons. It was the old man formula. Old man formula, that's funny. You take mass minus the protons, and you get the neutrons, right? So in this case, just going fully with this, 12 minus 6 protons means you have to have 6 neutrons. Because all this mass had to come from someplace, and that's what's in the nucleus. Okay, I'm gonna switch my pen color, tighter red. Carbon 12. Now, let's assume we're looking at carbon still, right? So its atomic number is 6, I expect 6 protons. And now, you'll notice that there's one more of those little blue circles in the middle. Actually, there's 2 more. Sorry, rather 1 more, my bad. What we're looking at here is an atomic mass of 13 units. So this is a different kind of carbon. It is just heavier. Doesn't mean it's not carbon, it just means it has more neutrons. Okay, so this, when we have a different isotope of carbon, we say it's carbon 13, whereas this up here was carbon 12. They're both carbon, one's just heavier, one's just lighter. Okay, now there's an interesting form of carbon, and you've probably heard about radiocarbon dating. If we do archaeological digs and we find wooden material that's buried down deep, or if we find an old part of a house that's been buried down deep in the soil, if there is still woody material, right, we've got within 60,000 years to figure out how old it is. It's kind of interesting. There's a kind of carbon, carbon 14, that we find in living things. Now, I served up the webpage on this a little while ago, and it's really, no, I don't want that, not photos. There we go. And it's a really neat article from How Stuff Works. And it talks about this weird version of carbon. You would expect carbon to be 12 all the time, right? Carbon 12 is the most common form. 6 protons, 6 neutrons. But look at this. You've probably heard about cosmic radiation, and this sounds fancy, like how the Fantastic Four and the comic books were created. We're going to make this a little simpler. The world is being hit with really energetic particles and waves of energy that we call radiation. And cosmic rays are hitting the planet all the time. I remember going to Science World, and they have a display where you can actually see cosmic rays hitting something that can detect them. Now, these cosmic rays, when they collide with certain atoms, can cause an energetic neutron, like kind of bump a neutron out of the nucleus. You could think of it as something bouncing around. And if that neutron, right, were to end up in nitrogen, so nitrogen becomes a little heavier, right? It becomes nitrogen 14. It's a little bit like, how can I describe this? There's a collision, and it's so energetic that it actually popped a proton out. You can see that proton going off to the side. Now, in the periodic table, let's just look at this for a second. Nitrogen is right beside carbon. So it normally has 7 protons in its nucleus. But if a really energetic neutron, which was dislodged from something else, bumped in to nitrogen, nitrogen could lose a proton, and if it loses a proton, 7 becomes 6. Now this is pretty interesting. That's how the nucleus works. The number of protons define what you are. Okay, so let's not get too technical. So what happens? A neutron that's energetic because of cosmic rays hits nitrogen 14, and a proton goes flying out, which is essentially hydrogen, by the way. When that neutron takes the place, you still have something that weighs 14, but now because you have one less proton, it's carbon. Carbon 14, you think about photosynthesis. Carbon, in the form of carbon dioxide, gets absorbed by living things all the time. So there's this form, this carbon 14 form that gets absorbed into plants. And then because of the food table, plants get eaten by the animals, and it becomes a kind of carbon that goes into living things. It's all about photosynthesis, primary producers, the plants, and primary consumers, the animals, and it ends up in us. Now here's what's really cool. Because carbon-14 isn't exactly stable, that proton that it gained, it can lose. And carbon-14, under those conditions, if you lose that proton, right, you end up becoming, it's something that we'll go through called beta decay. But it's pretty neat. And if you beta decay, you end up nitrogen-14. So we look at the amount of carbon-14 in things, we look at the amount of nitrogen-14 in things, and we can use that as a clock to figure out when something died. Because that carbon-14 essentially kind of falls apart and becomes nitrogen-14 in a process called beta decay, which we'll get into later. But it's really interesting because what we're talking about here are isotopes. Back to this. So here's carbon with the 6, and if it's going to become carbon-14, there's 8 circles in there. And it's not very stable. I'm going to tell you a secret in chemistry. And you might have seen this in the build an atom assignment that we did on, I believe that was on PHET Colorado, which is just neat. Normally a nucleus likes to have an equal amount of neutrons and protons. And when you start to get out of whack a little bit, in this case, it's 6 protons to 8 neutrons, it starts to get a little upset. And that's not a stable nucleus, which is why we get radioactive decay. Now, because there's 6 protons, there's still the 6 electrons. So isotopes have nothing to do with electrons, folks. They have to do with a greater number or a fewer number of neutrons in the nucleus. So this is a ratio where they're not equal. Normally they should be equal. Later on we'll talk about uranium, and I'll tell you that's really unequal when it comes to the neutrons. So our mass number is 14, so we call this carbon-14. Okay, so because there's different kinds of isotopes, we've got to have some way to write them down. So when you look at a typical element, letter E, right, for the element, and then we have the mass number written above and the atomic number written below. Now here's our 4 forms of this element, and if you're going to describe hydrogen properly in terms of isotopes, right, you could see that the atomic number is written as the subscript, so that's H1 with the subscript. The superscript, or the one going up in the air like Superman, that's going to be mass. So that's how you have to keep track of these things. Chemistry becomes a little more complicated, then we just all reveal another little layer, okay? So we've got hydrogen 1, 2, and 3. True story. Okay, so when it comes to writing down what you think a carbon should be, right, where we have 6 protons and 6 neutrons, pause the video for a second, speaking of 6s, and write down what you think carbon-12, carbon-13, and carbon-14 are, how they should be written. Pause, write it down, like you could pause, you're looking at the hydrogen examples here, figure out what that would be for carbon. Now, let's take a look at these ones here. Atoms of the same element, different masses, right? You're seeing an example of carbon in the first instance with 5 protons. Just 1 second here. Oops, I want to go back. So, in this case, you've got 5 neutrons, that's what I meant to say, because 6 plus 5, right? That's the only way you're going to get 11. This has 6 neutrons, and that's the one you're used to seeing. That's a very, very common form of carbon, right? 6 and 6 making 12. In this case, we have carbon-13, so 7 neutrons. 7 and 6, 13, and then carbon-14, which is an organic form of carbon. It's really excellent for dating things in living critters, but it falls apart after 60,000 years. There's nothing left. Carbon-14 becomes nitrogen-14, and then poof, that's it. There's not enough left. You can't measure past 60,000 years. You have to go and make more carbon-14, and there's your 14 right there. Okay, so an easier way to note it is like this: carbon-11, carbon-12, 13, and 14. right? Because if you had to write it with the superscripts and the subscripts, you'd probably go crazy. We all would. Okay? And isotopes have a different number of neutrons. Got that. Okay. So here's hydrogen, right? A very common form of it. 1 proton, 1 electron. Hey, there you go. Oops. All right, so I got ahead of myself. Got to go back. There we go. Let's look at hydrogen 1. Now, when you hear that hydrogen is just a proton, you can call hydrogen proton because all that's floating around in here is just a single proton, right? Hydrogen can technically float around as an ion. If it didn't have this electron outside here, this would be hydrogen 1 as a +1 ion, as a cation. But we'll get back to that later. This is hydrogen 1, most common form. Hydrogen 2 is known as deuterium, and you'll see in this case you've got a proton and you got a neutron, which is why you have atomic mass. Oops, I went too fast. Which is 1 proton, 1 neutron, 2 atomic mass units. Okay, got that. Here's tritium, and over here pretty much tells you why it has this atomic mass, right? But if you start to get too many neutrons, you can make nuclei unstable, right? And unstable atoms will undergo radioactive decay. So what have we got for isotopes? How many things form isotopes? Well, chlorine does it. There's chlorine-35 and there's chlorine-37, which means chlorine-37 has 2 more neutrons, right? By plus, I just mean 2 more. Now, chlorine has an atomic number of 17. That's that green poisonous gas, right? But the number of neutrons, and I've kind of given it away here, the difference between chlorine-35 and 37 has to be those 2 additional neutrons. So, if you do the math, chlorine-35, 17 protons, do the deductions, right? And this is that MAN formula, where you take the mass minus the protons equals, well, the rest of the weight in the nucleus, the neutrons. Poof, bada bing. And that's how you get 18. Nice. So, chlorine-37. Apply the MAN formula, right? Take the mass, deduct the protons, and that's 20 neutrons. So we're just applying the MAN formula over and over again. Now, when it comes to drawing and naming of isotopes, right? Oops. Sorry about that. I'm going to give you 2 examples here that you can take out for a spin, right? You go to boron, and you're looking at boron here as an atom, which is neutral, protons equal electrons. And in this one case over here, they're going to say, do a boron atom, just like you see in the periodic table. And then the one on the right, they're going to say, okay, here's boron, but with a mass of 13. Now, go to your periodic table, right? Help you out with this. Boron is atomic number 5. It's that green one in the second row, kind of right beside the sun there. All right. Given that information, you get to figure this one out. If that's boron 13, what is the difference in the neutrons? Now, they've thrown in the electrons. You should know what to write in for the electrons. I'll give you a hint. This thing has atomic number 5. Okay, folks, I promise to keep it somewhat short, but isotopes, just for the record, they're the same atom, but the number of neutrons is variable. It's not always the same. You saw 3 forms today of hydrogen, right? And they even, because they had 3 forms, they got cool names like deuterium and tritium. You saw that chlorine has isotopes, that there's an organic version of carbon called carbon-14 that actually breaks down and decays into nitrogen-14. But we'll talk about that one in a lot of detail later as we sort of finish up chemistry. But ladies and gents, that's it, and thanks for listening.